You've given a great, almost historical answer on the topic of the continuum hypothesis. And maybe that's a good place to go. We've touched on it a little bit, but it'd be nice to lay out what is the continuum hypothesis that Cantor struggled with. And I would love to also speak to the psychology of his own life story, his own struggle with it. It's the human side of mathematics is also fascinating.
Yes.
So what is the continuum hypothesis?
So the continuum hypothesis is the question that arises so naturally whenever you prove that there's more than one size of infinity. So Cantor proved that the infinity of the real numbers is strictly larger than the infinity of the natural numbers. But immediately when you prove that, one wants to know, well, is there anything in between? I mean, what could be a more natural question to ask immediately after that? And so Cantor did ask it, and he spent his whole life thinking about this question. And so the continuum hypothesis is the assertion that there is no infinity in between the natural numbers and the real numbers. And of course, Cantor knew many sets of real numbers. Everything in between, I mean, everything that's in that interval would be equinumerous with some set of real numbers. But we know lots of sets of real numbers. I mean, there's all these various closed sets, Cantor sets, and so on. There's Vitali set. We have all kinds of sets of real numbers. And so you might think, well, if the continuum hypothesis is false, then we've probably seen the set already. We just have to prove, that it's strictly in between. But it turned out that for all the sets that anyone ever could define or pick out or observe, for all the sets of real numbers, it was always the case either that they were countable, in which case they're equinumerous with the natural numbers or else finite, or they were fully equinumerous with the whole real line. And so they were never strictly in between. I mean, you're in this situation and you have hundreds, thousands of sets that are candidates to be in between. But in every single case, you can prove it's on one side or the other and not strictly in between. And so in every situation where you're able to figure out whether it's in between or not, it's always never strictly in between.
Now, Cantor was obsessed with this.
I think he was. Yeah, I'm not a historian, so I don't know the exact history.
Everything I've seen, it seems to be the question that broke him. I mean, just struggling with different opinions on the hypothesis within himself and desperately chasing, trying to prove it.
So he had a program for proving it, which has been affirmed in a certain respect. Of course, the continuum hypothesis holds for open sets. That's easy to see. If you have an open interval, then this is fully equinumerous with the whole real line. Any interval is equinumerous with the whole line. Because all you would need is a function, like the arctangent function or something that maps the whole real line into an interval. And that's a one-to-one function. So we know the open sets have the property that their non-trivial open sets are all fully equinumerous with the whole real line. So never strictly in between. But remarkably, Cantor proved it also for the closed sets. And that it's using what's called the Cantor-Bendixson theorem. So it's quite a remarkable result. It's definitely not obvious. And in this theorem actually was the origin of the ordinals. Cantor had to invent the ordinals in order to make sense of his Cantor-Bendixson process.
Can you define the open and the closed set in this context?
Oh, yeah, sure. So a set of reals is open if every point that it contains is surrounded by a little interval of points, the whole tiny little interval. But that tiny little interval is already just by itself equinumerous with the whole line. So that's why the question is sort of easy for open sets. A closed set is a complement of an open set. And there's a lot of closed sets that are really complicated of varying sizes. So, of course, any closed interval is a closed set, but it's not only those. There's also things like the Cantor set, which you get by omitting middle thirds. Maybe some people have seen this construction. Or you can imagine sort of randomly taking a lot of little tiny open intervals, all over the line and so on. So that altogether would be an open set, and the complement of it would be a closed set. So you can imagine just kind of tossing down these open intervals, and what's left over is the closed set. Those sets can be quite complicated. And they can have isolated points. For example, if the two open intervals were just kissing and leaving only the one point between them. But also you could have sequences that are converging to a point. That would also be a closed set, or a convergent sequences of convergent sequences and so on. That would be a closed set also.
The Cantor set is constructed by iteratively removing open intervals, middle thirds, like you mentioned, from the interval, and trying to see, can we do a thing that goes in between?
Right. So the question would be, can you produce a set that has an intermediate size, an intermediate
Yes.
cardinality, right?
Yes.
And Cantor proved with a closed set, no, it's impossible. Every closed set is either countable or equinumerous with the whole real line.
Mm-hmm.
And what the Cantor program for solving the continuum hypothesis was of sort of working up. So you did it for open sets and for closed sets, and you sort of work up. Maybe he wants to go into what are called the Borel sets, which are sort of combinations of open and closed sets. And there's a vast hierarchy of Borel complexity. And it turns out that the continuum hypothesis has been proved also for the Borel sets in this hierarchy. But then one wants to go beyond. What about more complicated sets? So there's this hierarchy of complexity for sets of real numbers. And Cantor's idea was to sort of work your way up the hierarchy by proving that the continuum hypothesis was more and more true for those more and more complicated sets based on our understanding of the earlier cases. And that has been carried out to a remarkable degree. It turns out that one begins to need large cardinal assumptions, though, in order to get to the higher realms, even at the level of projective hierarchy, which are sets that you can define by using quantifiers over the real numbers themselves. So you get this hierarchy on top of the Borel hierarchy, the hierarchy of projectively definable sets. And it turns out that if you have enough large cardinals, then the projective sets also are always either countable or equinumerous with the whole real line. And then one can try to go beyond this and so on. So I view all of those results, which came, in the past 50 years, the later ones, as fulfilling this Cantor idea that goes back, 120 years to his idea that we would prove the continuum hypothesis by establishing more and more instances for greater and greater complexity of sets. But of course, even with what we know now, it hasn't fully succeeded, and it can't because the hierarchy of complexity doesn't include all sets of real numbers. Some of them are sort of transcending this hierarchy completely in a way. And so the program can't ever fully be successful, especially in light of the independence results.
Yeah, well, spoiler alert, can you go to the independence result?
Sure.
So what does that mean? Continuum hypothesis was shown to be independent from the ZFC axioms of mathematics.
Right. So the ZFC axioms were the axioms that were put forth first by Zermelo in 1908 in regard to his proof of the well-ordered theorem using the axiom of choice. That wasn't fully ZFC. At that time, it was just Zermelo theory because there was a kind of missing axiom. The replacement axiom and the foundation axiom were added later, and that's what makes the Zermelo-Frankel axiomatization, which became sort of standard. Actually, there's another aspect, which is Zermelo's original theory allowed for the existence of elements, or these atoms, mathematical objects that are not sets, but out of which we build the set theoretic universe. Whereas set theorists today generally don't use elements at all. I argue that it's really the philosophy of structuralism that leads them to omit the elements, because it turns out that if you adopt ZFC axioms with elements, ZFCU it's called, or ZFA, then any structure that exists, any mathematical structure that exists in that set theoretic universe with the atoms is isomorphic to a structure that doesn't use the atoms at all. And therefore, you don't need the atoms if you're a structuralist, because you only care about the structures up to isomorphism anyways. And the theory is simply more elegant and clear without the atoms. They're just not needed. And so that's why today, when we talk about set theory, generally we're talking about the atom-free version, and ZFC has no elements. Okay, so we formulate the ZFC axioms of set theory. These are expressing the main principal ideas that we have about the nature of sets and set existence. And Cantor had asked about the continuum hypothesis in the late 19th century, and it remained open, totally open, until 1938.
And we should mention, I apologize, that it was the number one problem in the Hilbert's 23 set of problems formulated at the beginning of the century.
That's right.
Maybe you can comment on why did he put that as number one?
So Hilbert had introduced at his famous address at the turn of the century these list of problems that he thought could guide or were important to consider in the coming century of mathematics. I mean, that's how people talk about it now, although I'm not sure at all. Of course, I can't really speak for Hilbert at all, but if you were a very prominent mathematician, I find it a little hard to believe that Hilbert would have conceived of his list in the same way that we now take his list. I mean, having observed the century unfold, we know that that list of 23 problems did in fact guide whole research programs, and it was extremely important and influential. But at the time, Hilbert would have no reason to think that that would be true, and he was just giving a lecture and had a list of problems that he thought were very important. And so I would find it more reasonable to think that he was just making a list of problems that he thought were extremely interesting and important and fundamental in a way, without the kind of heavy burden of guiding this 20th century research, although it turns out that, in fact, that's exactly what they did. And we already discussed how Hilbert's views on the nature of set theory and the fundamental character, that quote where he said, "No one will cast us from the paradise that Cantor has created for us." So I think Hilbert was convinced by Cantor on the importance and the fundamental nature of the continuum hypothesis for the foundations of mathematics, which was a critically important development for the unity of mathematics. I mean, before set theory emerged as a foundation of mathematics, there were there's different subjects in mathematics. There's algebra and there's analysis, real analysis, and topology and geometry. And so there's all these disparate subjects with their own axioms, separate axioms, right? But sometimes it happens, like when you're proving, say, the fundamental theorem of algebra, that the complex numbers are an algebraically closed field that you can solve any polynomial equation in. But the proof methods for that theorem come from other parts of mathematics. There's topological proofs and so on. And so what is that? How does that work? I mean, if you have totally different axiom systems, but you're using results from one subject in another subject, it's somehow incoherent unless there's one underlying subject. So the unity of mathematics was provided by the existence of a mathematical foundation like set theory, and at the time it was set theory. And so it's critically important to be able to have a single theory in which one views all of mathematics as taking place to resolve that kind of transfer and borrowing phenomenon that was definitely happening. So that must have been part of Hilbert's thinking about why it's so important to have a uniform foundation, and set theory was playing that role at the time. Now, of course, we have other possible foundations coming from category theory or type theory, and there's univalent foundations now. So there's sort of competing foundations now. There's no need to just use one foundation, one set theoretic foundation, although set theory continues to, in my view, have an extremely successful meta-mathematical analysis as a foundation. I think is much more successful in set theory for any of those other foundations. But it's much less amenable, though, to things like computer proof and so on, which is part of the motivation to find these alternative foundations. So, so just talk about Hilbert, though. I think he was motivated by the need for a unifying foundation of mathematics, and set theory was playing that role. And the continuum hypothesis is such a core, fundamental question to ask. So it seems quite natural that he would put it on the list. There were other logic-related questions, though, like Hilbert's 10th problem is also related to logic. This is the question about Diophantine equations, and he asked to provide an algorithm to decide whether a given Diophantine equation has solution in the integers. So a Diophantine equation is just, it's maybe a fancy way of talking about something that's easy to understand, a polynomial equation, except it's not just one variable, many variables. So you have polynomials in several variables over the integers, and you want to know, can you solve it? So the problem is, as stated by Hilbert, provide an algorithm for answering the question whether a given polynomial equation has a solution in the integers. So he's sort of presuming that there is an algorithm, but he wants to know what is it? What is the algorithm? But the problem was solved by proving that there is no algorithm. It's an undecidable problem, like the halting problem. There's no computable procedure that will correctly decide whether a given polynomial equation has a solution in the integers. So that's quite a remarkable development, I think. So there were there's a few other logic-related questions on the list.
And so eventually, continuum hypothesis was shown to be independent from ZFC axioms, as we've mentioned. So how does that make you feel? And what is independence?
Well, one
and
should
what does
tell
that mean?
the story. The historical story is
Yes.
really quite
Yeah, it's
dramatic,
great.
I think, because Cantor poses the question, late 19th century.
Mm-hmm.
And then it's totally open. Hilbert asks about it, at the turn of the 20th century. Nobody has any clue. There's no answer coming. Until 1938, this is 4 decades later, right? So a long time. And Kurt Gödel proved half of it. What he proved is that if the axioms of set theory are consistent, then there is a set theoretic world where both the axiom of choice and the continuum hypothesis are true. So what he's doing is showing, this is called the constructible universe, Gödel's L. So he solved, this is the same result where he answers the safety question of the axiom of choice, but also for the continuum hypothesis. They're true in the same set theoretic universe. So if ZF without the axiom of choice is consistent, then so is ZFC plus the continuum hypothesis is the result. 1938. It's really such a beautiful argument. It's just incredible, I think, because he's building an alternative mathematical reality. That's the structure of the proof, is that, okay, if there's any mathematical reality, if there's any set theoretic world, then we're going to build another one, a separate one, a different one, maybe different. Maybe it's the same as the original one. It could be. If we started already in the one that he built, then it would be the same. But there's no reason to assume it was the same. So he has this kind of model construction method to build this alternative set theoretic reality, the constructible universe. And then he proves that the axiom of choice is true there, and also the continuum hypothesis is true there. And it's just amazing. Really beautiful argument. Okay, so then for the other part of the independence, that's only half of it, because Gödel shows basically that you can't refute the continuum hypothesis. But that's not the same thing as proving that it's true. He showed that if set theory is consistent without the continuum hypothesis, then it's consistent with the continuum hypothesis. So that's not the same thing as proving that it's true. And then it didn't come until 1963 when Paul Cohen invented the method of forcing and proved that if there's a model of set theory, then there's a model of set theory in which the continuum hypothesis is false. So Cohen also is giving us this extremely powerful tool for building alternative mathematical realities, is how I think about it. He's explained to us how to take any set theoretic world and build another different one in which the continuum hypothesis is false. The forcing extension.
It's just such a fascinating technique, tool of forcing. Maybe I'm anthropomorphizing it, but it seems like a way to escape one mathematical universe into another, or to expand it, or to alter it. So to travel between mathematical universes. Can you explain the technique of forcing?
It's all those things. It's so wonderful. I mean, that's exactly how I think about it.
And we should mention, maybe this is a good place to even give a bigger picture of it. One of your more controversial ideas in mathematics, as laid out in the paper, The Set Theoretic Multiverse, you describe that there may not be one true mathematics, but rather multiple mathematical universes. And forcing is one of the techniques that gets you from one to the other. So can you explain the whole shebang?
Sure. Let's get into it. So the lesson of Cohen's result and Gödel's result and so on, producing these alternative set theoretic universes, we've observed that the continuum hypothesis is independent and the axiom of choice is independent of the other axioms. But it's not just those two. We have thousands of independence results. Practically every non-trivial statement of infinite combinatorics is independent of CFC. I mean, this is the fact. It's not universally true. There are some extremely difficult, prominent results where people proved things in CFC. But for the most part, if you ask a non-trivial question about infinite cardinalities, then it's very likely to be independent of CFC. And we have these thousands of arguments, these forcing arguments that are used to establish that. And so how should we take that? I mean, on the one hand, if you have a theory and it doesn't answer any of the questions that you're interested in, okay, so what does that mean? If you're following what I call the universe view or the monist view, you might naturally say, well, look, ZFC is a weak theory, and there's the true set theoretic reality out there, and we need a better theory because the current theory isn't answering the questions. Everything's independent. And so that seems like a quite reasonable thing to take. If you think that that every set theoretic question has a definite answer and there's a unique set theoretic truth or a unique fact of the matter, right? This is the universe view.
And by the way, to reiterate, independent means it cannot be proved or disproved within this axiomatic system, within this theory.
Right. Exactly. So to be independent means you can't prove it, and also you can't prove that it's false. You
And
can't
you're
refute
saying
it.
that's why the statement is so traumatic or sad, that most of the interesting stuff, as you said, has been shown to be independent
Right.
of ZFC.
But that's an interesting way to put it, I think, because it reminds me of this when I was a graduate student in Berkeley. There was another graduate student who was working with a non-logic professor in C-star algebras or something like this. So it's a part of analysis or functional analysis. And they were looking at a question, and it turned out to be independent of CFC, right? And the attitude of this other professor was that, oh, I guess I asked the wrong question. But my attitude and the attitude of all the set theorists was, when you ask a question that turns out to be independent, then you asked exactly the right question, because this is the one, it's carving nature at its joints. You're adjudicating the nature of set theoretic reality by finding these two realms. You find one of these dichotomies. There's the worlds where it's true and the worlds where it's false. And so when you ask that question, that's to be celebrated. It means you asked exactly the right, interesting, fascinating question. So it's not a kind of bleak thing that you can't prove it and you can't refute it, and that's such a disaster. Rather, it means that you found this cleavage in reality, in mathematical reality, and it's good to know about those when they happen.
Carving nature at its joints. So what can you do about the things that are shown to be independent from ZFC? So
right.
what are the techniques?
So one thing is that because of the incompleteness theorem, we know that there's going to be, for any theory that we can write down, there's going to be things that we can't prove, true things we can't prove in it. So those things are going to be independent. And so we're already aware of the fact that there will always be these independence phenomenon for any theory that we write. And furthermore, some of those theories, we won't even be able to prove that they're consistent, like the consistency of the own theory. So that's called the consistency strength hierarchy. So it's a direct consequence of Gödel's second incompleteness theorem that for any theory we can write down, then towering over it is this incredibly tall tower of consistency strength, where the strength in theories aren't just adding another axiom, but they're adding another axiom even whose consistency was not provable in the previous layers of the hierarchy. And so how lucky we are to find the large cardinal axioms that instantiate exactly this feature of increasing consistency strength, this unending and extremely tall hierarchy of consistency strength of axioms. And it exactly fulfills the prediction that Gödel's theorem makes about that kind of thing, except that the axioms in the large cardinal hierarchy aren't metalogical, self-referential statements of the form that sometimes arise in the Gödel analysis, but rather they're professing existence of big infinities, these large cardinal axioms. And so it's such a welcome development. And yet, it's also known that the continuum hypothesis is independent of all of the known large cardinal axioms. So none of the large cardinal axioms we can prove, none of them can settle the continuum hypothesis. So the independence phenomenon is still there for things like the continuum hypothesis and the cardinal combinatorics that
So
I
you're
mentioned.
building this incredible hierarchy of axiomatic systems that are more powerful than the ZFC.
More powerful than ZFC, and then more powerful than that, more powerful than that, and so on. It keeps going forever, and it will never be finished.
And still, to this day, the continuum hypothesis is not.
It's not settled by any of the large cardinal axioms.
Wow. Wow. What does that? How does that make you feel? Is that will it ever be settled?
Yeah, well, it's part of my multiverse view, I guess. So, which we started by I was describing the universe view, which is the view that look, there are facts of the matter about all of these questions, and that it will turn out if you're a universe view person, which I'm not, but if you are, then you will hold that there is a right answer to the continuum hypothesis question, and there's a right answer to the large cardinal questions and so on, and that what we should be aiming to do is figure out this one true set theory. Okay. In contrast, I take the developments of set theory over the past half century or more as evidence that there isn't such a unique set theoretic reality. Rather, what we've been doing for decades now is producing more and more alternative set theoretic universes in which the fundamental truths are differing from one to the other, and that is the answer to the continuum hypothesis question. The fact that given any model of set theory, there's a forcing extension where the continuum hypothesis is true and another one where it's false. You can sort of turn it on and off like a light switch. And that's the fundamental nature of the continuum hypothesis, is that you can have it or you can have the negation as you like within a very closely related set theoretic world. Wherever you happen to be living, there's a closely related one where CH is true, where the continuum hypothesis is true, and one where it's false. And that itself is a kind of answer. It's not a singularist answer, a universe view answer. It's a pluralist answer. And this led me to my views on the multiverse view of set theory and pluralist truth, namely the fundamental nature of set theoretic truth has this plural character in that there isn't a singular meaning to the fundamental terms, but rather there's this choice of alternative set theoretic universes that have different truths.